Okay, so the reaction shown right here, I still haven't learned all the names of the molecules or how to pronounce them or say them, but we'll go with what we have. Was studied and the following data were obtained. So we have the concentration of the iodide, I think, because this is an ion of iodine, and monochlorous or something like that. I should probably not say the names. I don't want to confuse you guys. But the first question is, what is the rate law? So it basically asks us to write the generic form of the rate law, which is going to be K times I, concentration of I minus to the N, times the concentration of OCl minus to the M. And we may have a negative in front as well because they're both going to decrease, right? So we'll put that negative right there. Now calculate the value of the rate constant. All right, so if actually no, because we won't have the negative because the concentrations are all positive. Let's now calculate the value of the rate constant. So to calculate the value of the rate constant, we have to do a couple things. So I'm going to go over here and we're going to first find a situation in which OCl doesn't change. So for example, we can say okay, well, I'm thinking that here doesn't change, so we can use these two. But then is there a place where where I doesn't change? And I don't see it anywhere. I don't see it anywhere. I see another place where OCl doesn't change. Perhaps that's going to be enough. We'll see. Okay, so let's see. We can say 7.60 times 10 to the negative 2 m over s, molarity over seconds, is going to be equal to K times the concentration of OCl minus cancels. So we're just going to say it's going to be equal to 0.080 molarity. And then we're going to divide it by, actually we don't even need to divide it. That's it. Now we can say that K is going to be equal to 7.60 times 10 to the negative 2 molarities over seconds divided by 0.080 molarities. So our K is really going to be equal to what? It's going to be equal to 1 over seconds. However, our rate law is not exactly like that. There's an n here, and so we can't just willy-nilly do what we did. And then there's going to be a 0.20 molarity to the m. Okay? So actually, I do want to write it because I think I'm skipping steps and then I'm writing things that are not necessarily correct. And then I'm going to divide by 3.8. 3.8 times 10 to the negative 2 m over s, molarities over seconds, times divided by k. So that's going to give me a way to find 0.040 to the n, and then this stays the same, right? So actually this is gonna cancel out. The K is gonna cancel out. And 7.6, that's gonna be 2, is equal to 2 to the n, so n is equal to 1. Once we have n is equal to 1, now all bets are off because, well, maybe not. Let's see. So we chose, let's say this is experiment 1, 2, 3, and 4. So choosing experiments, and what do we have? 1 and 2. 1 and 2, we have certain things, right? Now, I want to choose other experiments as well. So now what I want to do is I want to do other things. I want to look at, let's say this one, right? So if we look at this one, what are we going to get? Well, now we're going to get 0.040. That's still molarities. That's for iodine. So we want to actually start from 3.80 times 10 to the negative 2 molarity per second. That's going to be equal to K and 0.0. So we choosing experiments 3 and 4. We're moving this. So we're going to move this down just a little bit. And this right here. So now what are we going to do? Well, we have our K here. And our K is just going to stay K. And now we have 0.040 molarities, right? That's for iodine. And we already figured out that it's to the power of 1. So that's kind of nice. And then we have 0.10 to the m. And now we want to divide it by experiment 3, because we didn't choose 3 and 4. I think you're noticing that I'm kind of tired. 2 and 3, because it's taking me a while and and I'm missing steps. But let's keep going. 9.50 times 10 to the negative 3 here, newtons over seconds. And we have our K here, and we're going to put 0.020 molarity still to the first power. And here this was supposed to be a 2. So this is 0.10 to the, what is this going to be, to the m again. And so now what's going to happen? Well, this is going to cancel out. I am going to execute 3.8 times 10 to the negative 2. And I'm going to use this because now I'm going to divide by 9.5 times 10 to the negative 3. And we get 4. So here I'm going to write 4 is equal to, let's see. This I know is 2, and then time is going to be 2 to the m. Now if I divide 2 both sides, I get 2 is equal to 2 to the m, which means that m is equal to 1. And so now that we have that, we can use any of these. So I'll use experiment 4. So using any experiment, right? Calculate the value of the rate constant. We can say, let's say we use the first one. So we're going to say that 7.60 times 10 to the negative 2 molars per second. That's going to be equal to K multiplied by 0.08 molarity and 0.20 molarities, and so you get your K. That's gonna be equal to what? So hold on, let's do this right. 7.6 times 10 to the negative 2, all of it divided by 0.08 times 0.2. We get 19 over 4, same thing as 4.75. The units are going to be m to the negative 1, s to the negative 1. And so this is going to be the answer for the rate constant. And now calculate the initial rates for an experiment where both I and OCl are initially present at 0.14 molarity. And so this last part, what color can I do it in? I'll do it in this color right here. That last part, and I'll just do this. All we have to do is we have to use the formula we just filled in. So rate is equal to our K, which is 4.75. So 4, and I'll color code it for you. 4.75, 1 over ms, right here, times 0.14 molarity and 0.14 molarity. So actually, if I want to color code it, we want 0.14 molarity, so big M, and here as well, 0.14 molarity. And what do we get? So my answer multiplied by 0.14 squared, that's going to be equal to 0.0931 moles per second. So at least the units work out, right? Now I'm gonna input everything into the computer and see that I did it right. But this is the process. I hope you understood something, and I'll see you next time.